Lambda is the eigenvalue of A corresponding to the eigenvector x. Then we have to prove that lambda power n is also an eigenvalue of A power n corresponding to the eigenvector x. So we prove this theorem by mathematical induction. What is the mathematical induction first? We have to prove the statement for every value of n. Now we assumed that it is true for n equals to 1, and we prove this the statement is true for n equals to 2, and also we assume that it is true for n equals to k, and we prove that it is true for n equals to k plus 1. Hence we conclude that it is true for every value of n. This is the mathematical induction. So we assume here in this, we assume that it is true for n equals to 1. That is, if lambda, that means lambda is the eigenvalue of A corresponding to the eigenvector x. Then by the definition of eigenvalue, we have Ax equals to lambda x. Take this as equation number 1. Now we are going to prove that it is true for n equals to 2. That means lambda square is the eigenvalue of A square. For that we multiply by A on both sides to the equation 1. So A into Ax equals to A into lambda x. So A square x equals to lambda into, rechange this lambda into Ax. So now A square x equals to lambda into, instead of Ax we are writing lambda x, since Ax equals to lambda x from the equation 1. So A square x equals to lambda square x. So we get lambda square is an eigenvalue of A square corresponding to the eigenvector x, because A square equals to, what is the eigenvalue and eigenvector definition? Ax equals to lambda x. Then lambda is the eigenvalue of the matrix A and x is the corresponding eigenvector. So in the same way we have here A square x equals to lambda square x. So lambda square is the eigenvalue of A square corresponding to the eigenvector x. So now we proved that it is true for n equals to 2. Now assume that it is true for n equals to k. That means A power k into x is lambda power k into x. We assume that it is true for n equals to k. That means lambda power k is the eigenvalue of A power k. If lambda power k is the eigenvalue of A power k, by the definition we get A power k into x equals to lambda power k into x. Now again we have to prove that it is true for n equals to k plus 1. For that we multiply by A on both sides. So A into A power k into x equals to A into lambda power k into x. Now A into A power k is A power k plus 1 into x equals to lambda power k into Ax. Again Ax equals to lambda x since from 1. So we get A power k plus 1 into x equals to lambda power k plus 1 into x. So A power k plus 1 into x equals to lambda power k plus 1 into x. By the definition, lambda power k plus 1 is the eigenvalue of A power k plus 1 corresponding to the eigenvector x. So we proved that it is true for n equals to k plus 1. Hence, we conclude that it is true for every value of n. That means lambda power n is an eigenvalue of A power n corresponding to the eigenvector x. So this is very important theorem. And coming to the second theorem, the eigenvalues of an idempotent matrix are either 0 or unity. The eigenvalues of an idempotent matrix are either 0 or unity. That means we say that lambda is the eigenvalue of the matrix A. So if A is an idempotent matrix, then the lambda value, then eigenvalue will be either 0 or unity. That means 0 and 1. If A is an idempotent matrix. What is an idempotent matrix? A square. If A square equals to A, we say that A is an idempotent matrix. Now, suppose lambda be the eigenvalue of A corresponding to the vector x, then by the definition we have Ax equals to lambda x. Take this as equation number 1. Now pre-multiply by a to the equation 1 on both sides. So we get a into ax equals to a into lambda x. So a square, so a square x equals to lambda into, see the second step, a square x equals to lambda into ax, and a square x equals to lambda into, since ax equals to lambda x from equation 1, so ax equals to lambda x. So we get a square x equals to lambda square x. Since A is an idempotent matrix, A square, that means A square equals to A, condition satisfied. So instead of A square, we can write Ax equals to lambda square x. Now see the definition of eigenvalues and eigenvectors. If Ax equals to lambda square x, then by the definition, lambda x equals to, now see, again we just instead of ax from the equation 1, ax equals to lambda x equals to lambda square x. So lambda x minus lambda square x equals to 0. Lambda minus lambda square into x equals to 0. Since x not equals to 0, eigenvector is not a 0 vector. So it is non-zero vector always. So lambda minus lambda square equals to 0. So now what are the factors of lambda? Lambda equals to 0 or lambda equals to 1. If A is an idempotent matrix, the eigenvalues of the idempotent matrix are either 0 or 1. Hence we proved it. Now coming to the next theorem, the sum of the, very important theorem this one, the sum of the eigenvalues of a matrix is its trace. We use this statement to prove so many problems. The sum of the eigenvalues of a matrix is its trace, and the product of the eigenvalues is the determinant of A. The sum of the eigenvalues is trace of the matrix, and the product of the eigenvalues is determinant of the depth of the matrix. Now to prove this statement, we take the order of 3 by 3 matrix. So what, let A equals to order of 3 by 3 matrix, which are the elements are A11, A12, A13, A21, A22, A23, A31, A32, A33. Now to find the eigenvalues of this matrix, any matrix A, we take the characteristic equation. What is the characteristic equation? Determinant of A minus lambda equals to 0. Now first find the determinant of A minus lambda I, that equals to, what is A? A11 to A33. Now det of A minus lambda I equals to A11 minus lambda, A12, A13, A21, A22 minus lambda, A23, A31, A32, A33 minus lambda. Now find the determinant. We get, suppose, A11 minus lambda into, see, corresponding row, corresponding column. So multiply A22 minus lambda into A33 minus lambda minus A23 A32, like this. Next, minus of second one, corresponding row, corresponding column. If you eliminate A12 into A21 into A33 minus lambda minus of A23 into A31. If you find the determinant A13 like this, A13 into corresponding row and corresponding column, eliminate the, now det of this A21 into A32 minus A31 into A22 minus lambda. Okay. Now if you simplify this, we get lambda minus lambda cube minus, see here minus lambda, here minus lambda, here minus lambda we get. So if you simplify this determinant, we get like this. Lambda cube coefficient will be -1 and plus lambda square coefficient will be A11 plus A22 plus A33 minus lambda coefficient will be something, you will get it. Okay, so this is consider statement 1. Now suppose lambda 1 comma lambda 2 comma lambda 3 be the eigenvalues of A. Suppose lambda 1, lambda 2, lambda 3 be the eigenvalues of A. That means what? Lambda 1, lambda 2, lambda 3 are the roots of the characteristic equation. You know this one, suppose eigenvalues 1 comma 2 comma 3 means what this 1 comma 2 comma 3 are the roots of the characteristic equation like this. Suppose if you find any, if you take any matrix, you will get the characteristic equation like this. If you solve this characteristic equation, you will get the eigenvalues. This means what? These three are the roots of the equation. Just I am taking the example of characteristic equation. I don't know these are the exactly roots. Just I am taking the example. Now, here in the same way, suppose lambda 1 comma lambda 2 comma lambda 3 be the eigenvalues of A. That means those lambda 1, lambda 2, lambda 3 are the roots. So for that, how can we write modulus of A minus, determinant of A minus lambda I equals to minus 1 whole cube into the roots of lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda 3. Okay. So if you simplify that, minus lambda cube plus lambda square into lambda 1 plus lambda 2 plus lambda 3 minus and so on. Just multiply the above, multiply this equation, this last. If you multiply, you will get this expression minus lambda cube plus lambda square into lambda 1 plus lambda 2 plus lambda 3 minus lambda square minus lambda into that some, the coefficient of lambda will be get some other way. Now consider this as equation number 2. Now, from 1 and 2, compare 1 and 2, compare 1 and 2 and compare the coefficient of lambda square. So that is lambda 1 plus lambda 2 plus lambda 3 equals to A11 plus A22 plus A33. See, lambda cube coefficients are same. Lambda square coefficients are only different. So we are considering that one only. Lambda 1 plus lambda 2 plus lambda 3 equals to A11 plus A22 plus A33. So what you assumed from this expression, lambda 1 plus lambda 2 plus lambda 3 equals to A11 plus A22 plus A33. That means sum of the eigenvalues equals to trace of the matrix A. See, A equals to what you assumed, A11, A12, A13. See, A21, A22, A3, A23, A31, A32, A33. What is A32, A33? What is the trace of A? Sum of the diagonals is nothing but the trace of A. So, A11 plus A22 plus A33. So, hence we conclude that sum of the eigenvalues equals to trace of A. Now we have to prove that the product of the eigenvalues equals to determinant of A. For this, put lambda equals to 0 in A minus determinant of A minus lambda equals to second equation. In the second equation, in this second equation, we put lambda equals to 0. So, if lambda equals to 0, what you get? Det of A minus lambda is converted into det A since lambda equals to 0. Minus 1 cube into minus lambda 1 minus lambda 2 minus lambda 3. Now, det of A equals to lambda 1 into lambda 2 into lambda 3. So, the product of the eigenvalues equals to determinant of A. Hence, we proved that statement, which is sum of the eigenvalues equals to trace of A and product of the eigenvalues equals to determinant of A. Now, next theorem, if lambda is the eigenvalue of a non-singular matrix A corresponding to the eigenvector x, then lambda power minus 1 or 1 by lambda is an eigenvalue of A inverse corresponding to the eigenvector x. See, I just want to tell you, if any theorem which we are going to prove, just what is the given statement and what is the our aim. That first you write one side. Given statement, if lambda is the eigenvalue of a non-singular matrix A, this is non-singular matrix, then our aim is lambda power minus 1 is the eigenvalue of A inverse. This we have to prove. Just keep one side. Then you can understand. This is the outline of the theorem. Now, given statement, by using the given statement only we can prove the statement, any statement. So since A is A, and one more thing here, the matrix which we considered, that is a non-singular matrix. Non-singular matrix means what? Determinant of A is not equals to 0. So let remember this point, that of A is not equals to 0. Already by the above theorem what we learned, determinant of A is nothing but the product of the eigenvalues. So here det A is not equals to 0. That means product of lambda 1, lambda 2, lambda 3, product of these eigenvalues must be not equals to 0. Must be not equals to 0 means any one of the eigenvalue is not equals to 0. If any one of the eigenvalue is not 0, then determinant of A, product of the eigenvalues is not 0. So that means lambda is not equals to 0. Okay. So remember this point. Now, given that lambda is the eigenvalue of A, then by the definition we have Ax equals to lambda x. Take that is equation number 1. Multiply by A inverse on both sides. So, A inverse into Ax equals to, so multiply by A inverse on both sides to this equation. So, A inverse into Ax equals to A inverse into lambda x. A inverse into Ax equals to lambda into A inverse x. So, A inverse into A means Ix equals to lambda into A inverse x. So, x equals to lambda into A inverse x. Just go step by step, you can understand easily. So now cross multiply 1 by lambda into x equals to A inverse x. So finally A inverse x equals to 1 by lambda into x, where lambda not equals to 0. How do you say lambda not equals to 0? Since A is not singular. That means determinant of A is not equals to 0. Since product of the eigenvalues equals to determinant of A, so that no eigenvalue is 0 in this. So lambda is not equals to 0. So A inverse equals to lambda inverse x. By the definition, compare with the definition, so that lambda inverse is the eigenvalue of A inverse corresponding to the eigenvector x. Now, next theorem. This is also very important theorem. If lambda is the eigenvalue of a non-singular matrix A, then determinant of A, det A by lambda is the eigenvalue of the matrix adjoint A. Determinant of the matrix adjoint A. Det A by lambda is the eigenvalue of which matrix? Adjoint A matrix. So, given that lambda is the eigenvalue of a non-singular matrix A, so same, non-singular matrix means det A not equals to 0. Since product of the eigenvalues equals to determinant of A, so since det A is not equals to 0, that means no eigenvalue is 0. That means lambda not equals to 0. So, lambda is the eigenvalue. Since from the statement lambda is the eigenvalue of the matrix A, so by the definition Ax equals to lambda x. Now, we have to prove that det A by lambda is an eigenvalue of adjoint A. So that take adjoint A and multiply by adjoint A to Ax equals to lambda x on both sides. So adjoint A into Ax equals to adjoint A into lambda x. Adjoint A into A, associative. Matrix have associative property. So adjoint A into x equals to lambda into adjoint A into x. So adjoint A into A equals to det A into I. How? We know that A inverse equals to adjoint A by det A. So adjoint A equals to A inverse into det A. Okay. Now adjoint A into multiply with A. Adjoint A into A equals to A inverse into det A into A. Okay, that means A inverse into A into det A. So A inverse into A means I into det A. So finally adjoint A into A equals to I into det A. So for that, adjoint A into A means det A into I into X equals to lambda into adjoint AX. So det A into I means det A into X equals to lambda into adjoint A by X. Now cross multiply by lambda. So det A by lambda into X equals to adjoint AX. So adjoint A into X equals to det A by lambda into X. By the definition, det A by lambda is the eigenvalue of adjoint A. Okay, hence the theorem is proved. Next theorem, if lambda is the eigenvalue of here, same first theorem is repeating here, but instead of lambda power n, here they have given lambda 1 power k, lambda 2 power k, and so on, lambda n power k are the eigenvalues of a power k. See, we know that the number of eigenvalues is depending on the order of the matrix. So suppose if it is order of the matrix A is 2 by 2, the eigenvalues will be 2. The number of eigenvalues will be 2. If 3 by 3 matrix, the number of eigenvalues will be 3. Like that we get here how many eigenvalues are there in this matrix, in this statement, n number of eigenvalues. That means the matrix which you have taking A is order of n by n. So here also we prove this by mathematical induction. If lambda power, see one more time the statement, read the statement once again. If lambda 1 comma lambda 2 and lambda 3 and so on, lambda n are the eigenvalues of A, then lambda 1 power k, lambda 2 power k, and so on, lambda n power k are the eigenvalues of A power k. Okay. See, for this, let lambda I equals to, now I am just taking all the eigenvalues are nothing but lambda I am taking. Let lambda I equals to lambda 1, lambda 2 and so on, lambda n eigenvalues of A corresponding to X. Then by the definition we can write what we can write, Ax equals to lambda I into X. Lambda I means here every what are the eigenvalues, what we assume, lambda I means lambda 1, lambda 2 and so on, and so on, lambda n all are the eigenvalues and comes under the lambda I. So by the definition, Ax equals to lambda I x. Now by the same, what is the theorem 1, just we changed, instead of lambda here you put lambda I, that's it. Assumed that it is true for n equals to 1 and we prove that it is true for n equals to 2. That means pre-multiply by A on both sides. We prove that for 2 lambda I square. See, step by step, A square x equals to lambda I square x. That means lambda I square is the eigenvalue of A square. That means lambda 1 square, lambda 2 square, lambda 3 square and so on, lambda n square are the eigenvalues of A square corresponding to the eigenvector x. Instead of all this, I am just putting lambda I. So again, it is true for n equals to k. So that means we assume that it is true for n equals to k. That means we get a power k into x equals to lambda I power k into x. Hence we proved that it is true for n equals to k plus 1. To prove that it is true for n equals to k plus 1, again we multiply with a to this statement, a into lambda I power k into x. So we get a power k plus 1 into x equals to lambda I power k into x. X is nothing but what? Lambda I x. So lambda I power k plus 1 into x. So here a power k plus 1 into x. So lambda I power k plus 1 is the eigenvalue of a power k plus 1. Hence Okay, hence it is true for every n value. So hence we conclude that lambda I power k, lambda I power k is the eigenvalue of a power k. Lambda I power k means lambda 1 power k, lambda 2 power k and so on, lambda n power k are the eigenvalues of a power k corresponding to the eigenvector x. Now, next theorem. If lambda is the eigenvalue of an orthogonal matrix A, then 1 by lambda is also an eigenvalue of the same matrix. That means A. 1 by lambda is also an eigenvalue of A. If lambda is the eigenvalue of, if lambda is the eigenvalue of, lambda is the eigenvalue of C, lambda is the eigenvalue of A, then 1 by lambda is also eigenvalue of A, but A should be an orthogonal matrix. A is orthogonal matrix means what? What is an orthogonal matrix? And that means A into A transpose. If A into A transpose equals to A transpose into A equals to I, then A is an orthogonal matrix. So A into A transpose equals to A transpose into A. So A into A transpose equals to I. That means A transpose equals to A inverse or A inverse equals to A transpose. We have one condition. Now coming to the proof of the theorem, we know that if lambda is an eigenvalue of A, then 1 by lambda is an eigenvalue of A inverse. In the previous theorem, we have just seen in the previous theorem. If lambda is the eigenvalue of a non-singular matrix A, then 1 by lambda is also an eigenvalue of A inverse. Since A is an orthogonal matrix, then we have the condition just now I explained here. Okay. So since A is an orthogonal matrix, that means A inverse equals to A transpose. So if lambda is an eigenvalue of A, then 1 by lambda is an eigenvalue of A inverse. Since A inverse equals to A transpose, so that what we can write? Lambda, if lambda is the eigenvalue of A, then 1 by lambda is an eigenvalue of A transpose. Okay. And 1 by lambda is an eigenvalue of A also. I just coming to the theorem. This is one theorem. A and A transpose have the same eigenvalues. Same eigenvalues. You see, suppose, for example, 1, 2, 3, 4. For this matrix, you find the eigenvalues. Same eigenvalues you get transpose of this matrix 1, 3, 2, 4. If you find the eigenvalues, same eigenvalues we are getting. So A and A transpose have the same eigenvalues. So if 1 by lambda is the eigenvalue of A transpose, then 1 by lambda is also an eigenvalue of A. Okay. If so, hence we conclude that if lambda is the eigenvalue of an orthogonal matrix, then 1 by lambda is also an eigenvalue of A. Okay, only just to prove this statement, what is the condition you have to remember? A inverse equals to A transpose. That is the main point of this theorem. Okay, next theorem. Now see, A and A transpose have the same eigenvalues. Just I used this condition in the previous theorem, right? So A and a square matrix have the one second. A square matrix A and its transpose A power T have the same eigenvalues. That we have to prove that. We know that A minus lambda I transpose equals to. Why you are taking this condition A minus lambda I? Because here we are talking about the eigenvalues. So eigenvalues, how to find the eigenvalues? Taking the characteristic equation, that is A minus lambda I. So first we are just taking A minus lambda I transpose. What is A minus lambda I transpose? If you apply transpose to A minus lambda I, what you get? See, A transpose minus lambda I transpose. How do you get? By the properties of transpose. A plus R minus B transpose equals to A transpose plus R minus B transpose. Same, we applied the property to this A transpose, what you are getting? A transpose minus lambda I transpose. A transpose minus, since lambda is the scalar, so lambda power transpose, scalar transpose means scalar only, so lambda I transpose. Identity mat, the transpose of identity matrix is same identity matrix, so A transpose minus lambda I. So, A minus lambda I transpose equals to A transpose minus lambda I. Now, take the modulus or determinant on both sides. So, determinant of A minus lambda I transpose equals to determinant of A transpose minus lambda I. We know that det A is equals to det A transpose. Suppose see 1, 2, 3, 4. What is the determinant of this? 4 minus 6 minus 2. And now transpose chain 1, 3, 2, 4. What is this? 4 minus 6 minus 2. So the det of A and A transpose is same. So transpose of A minus lambda I is not the determinant of transpose of A minus lambda I is nothing but det of A minus lambda I. So A minus lambda equals to A transpose minus lambda I. Both are equal means if suppose modulus of A minus lambda equals to 0, if and only if modulus of or determinant of A transpose minus lambda equals to 0. See, by the characteristic equation definition, determinant of A minus lambda equals to 0. That means lambda is the eigenvalue of A. If and only if lambda is the eigenvalue of A transpose. So, hence A and A transpose. See, if lambda is the eigenvalue of A, then lambda is the eigenvalue of A transpose. So, A and A transpose have the same eigenvalues. Now, next theorem. The eigenvalues of a triangular matrix. We use this theorem statement to solve so many problems. Very important one. The eigenvalues of a triangular matrix are just the diagonal elements of the matrix. To prove this, consider the matrix A equals to A n by n matrix, A1 general matrix A11, A12 and so on, A1n, 0, A22, A23 and so on, A2n, 0, 0, A33, A31 and so on, A3n and so on, ANN. Be the triangular matrix. Upper triangular matrix be the upper triangular, or else you can take lower triangular matrix, or you can take just the triangular matrix also. Now, we are talking about the eigenvalues of the triangular matrices. So that take the characteristic equation, that is modulus of A minus lambda equals to 0 is the characteristic equation. So modulus of A minus lambda equals to modulus of, what is A? Find the determinant. A11 minus lambda, A12 and so on, A1n. Just the diagonal, subtract lambda from the diagonal elements only. So we get it. Now find the determinant of this. You will get A11 minus lambda A22. See, if you find this determinant of this, what you get? A11 minus lambda det of. Okay, det of law A22 minus lambda A23 and like that. Again for this. So A11 minus lambda into A22 minus lambda into A33 minus lambda into like this equals to 0. So equals to 0 means lambda equals to A11. See, lambda equals to A11 equals to 0, A22 minus lambda equals to 0 and so on, An minus lambda 0. So for this lambda equals to A11 comma A22 comma A33 and so on, Ann. A11, A22, A33 are the eigenvalues. A11, A22, A33 are what? Just the diagonal elements of the matrix here only, right? So the eigenvalues of a triangular matrix are just the diagonal elements of the matrix. Now, this theorem is for complex matrices. So, till previous theorem, those are the properties of the eigenvalues. Now, In the complex matrix, this theorem is related to the complex matrix. The eigenvalues of a Hermitian matrix are always, the eigenvalues of an Hermitian matrix are always real. So what is Hermitian matrix? Then the eigenvalues of, we have to prove that the eigenvalues of Hermitian matrix are real. What is Hermitian matrix? If A is any square matrix, then A power theta equals to A is nothing but Hermitian matrix. A power theta equals to A, then it is Hermitian matrix. I just written here. See, and since A is Hermitian, that means A power theta equals to A. The eigenvalue of this type of matrix are real numbers that we have to prove. Now, suppose let lambda be the eigenvalue of eigenvalue of a Hermitian matrix here. Hermitian matrix A corresponding to the eigenvector x, then by the definition we have Ax equals to lambda x. Now, take the conjugate and transpose on both sides. What is A power theta first of all? A bar transpose. This is the A power theta. Now, so A power theta, A power theta is nothing but transpose of conjugate of the matrix. So, now we pre-multiply by x power theta on both sides. So, x power theta into A into x equals to x power theta into lambda x. Now, again take first pre-multiply, here pre-multiply and then take the conjugate transpose, that is power theta on both sides. Here, these steps come here. So for first equation, pre-multiply by x power theta. Then after, take the conjugate and transpose on both sides. So x power theta ax whole power theta equals to x power theta lambda x whole power theta. We know the properties of theta. AB whole power theta equals to like transpose only. B power theta into A power theta. And also one more property, A power theta into whole power whole power theta equals to A. Okay. So by using this property, what you get? X power theta into A power theta into x power theta that equals to x power theta lambda power theta x power theta power theta. X power theta into A power theta. What do you get A power theta? Since A is Hermitian, that means A power theta equals to A. So instead of writing A power theta, you can write A. X power theta into A into x equals to x power theta into lambda power theta means lambda is the scalar. It may be real number or it may be complex number. So lambda bar you will get. Lambda bar into x power theta means x. That lambda may be real or complex. Now we are going to prove that it is not complex number, it is real number only. So lambda power theta, you'll get lambda bar. If it is real number, after taking bar is nothing but 2 real number only. So x power theta lambda x. Since ax equals to lambda x, so x power theta into lambda x equals to x power theta lambda bar x. So x power theta into x into lambda equals to x power theta x lambda bar. So x power theta into x take common, we'll get lambda minus lambda bar equals to 0. So lambda equals to lambda bar. Lambda equals to lambda bar when this condition satisfies. Suppose if lambda equals to 2i, what will be the lambda bar? Minus 2i. It's conjugate bar means. Now is it lambda equals to lambda bar? No, lambda is not equals to lambda bar. If lambda is the complex number. Suppose lambda equals to real number. Lambda equals to 2 only. Okay. Lambda bar. What you'll get? 2 means 2. Real number 2. Lambda bar means 2 only. So if lambda is the real number, we get lambda equals to lambda bar. So here lambda equals to lambda bar we get. by the calculation. So hence we conclude that lambda is the real number to satisfy this condition. Lambda is the only real number. So hence we prove that the eigenvalues of a Hermitian matrix are all real. In the same way, the eigenvalues of a skew Hermitian are purely imaginary or zero. See the material which I sent. In that, along with this video, I will attach the scanned copy. You go through the theorems. So, the eigenvalues of a skew Hermitian matrix are purely imaginary. So, in that theorem, we just considered the skew Hermitian. What is the skew Hermitian matrix? A power theta equals to minus A. Till this, the statements are same. Till which statement? Till this the statements are same. Sorry, here till this. So here a power theta, in this a power theta, instead of a power theta, you just replace minus a. So after replacing minus a here, we just here I just write a power x power theta minus a power theta equals to minus a, right? Minus x power theta into a into x equals to x power theta lambda bar x. So after simplifying, we get lambda plus lambda bar equals to 0. Okay, lambda plus lambda bar equals to 0 when you get, if it is purely imaginary value and a complex number. Suppose lambda equals to 2i. What will be the lambda bar? Minus 2i. Purely imaginary part. In the complex part, only imaginary part. Suppose if you take lambda equals to 2 plus 2i, lambda bar what you get? 2 minus 2i. Will not get. Lambda plus lambda bar equals to 0 will not get. Only imaginary value only. In the complex number, only imaginary value. Suppose lambda equals to 2i, the lambda bar minus 2i. So lambda plus lambda bar, what you get? 0. So this condition satisfied. So lambda plus lambda bar equals to 0 satisfies only when lambda equals to imaginary or else lambda equals to 0. Hence we conclude that the eigenvalues of a skew Hermitian matrix are purely imaginary or 0. In the same way, the eigenvalues of unitary matrix have absolute value 1. Absolute value 1. See, unitary matrix. What is unitary matrix? What is unitary matrix? A power theta into A equals to A into A power theta equals to I. Okay. So, since this is the condition, you just remember. So, eigenvalues of unitary matrix. Suppose lambda is the eigenvalue of unitary matrix A. By the condition, by the eigenvalues definition, Ax equals to lambda x we get. So, now take the power theta on both sides. Ax power theta equals to lambda x power theta. So, we get x power theta into A power theta equals to lambda bar into x power theta. Okay. Or x power theta into lambda power theta. So x power theta into a power theta equals to x power theta into lambda bar. So now 2 and 3. This is equation number 1. Take this is equation number 2. Multiply these two. Left sides. Ax into x power theta into a power theta equals to lambda x into x power theta into lambda bar. So here x into a power theta into x power theta equals to lambda into lambda bar into x power theta. See x into a power theta means I. Since A is unitary matrix by taking this condition, x power theta equals to lambda into lambda bar into x power theta. From this, you just take common x into x power theta. By take the associative law, you just rearrange. So x into x power theta equals to common, if you take common, 1 minus lambda into lambda bar equals to 0. So since x into x power theta not equals to 0, so 1 minus lambda into lambda bar equals to 0. That means lambda into lambda bar equals to 1. Lambda into lambda bar means what? What is lambda into lambda bar equals to 1? Modulus of lambda equals to 1. So the absolute modulus of lambda equals to 1 means the absolute value 1. So the eigenvalues of unitary matrix have absolute value 1. So these are the important theorems in the eigenvalues and eigenvectors concept. Go through this. You can expect one theorem along all from all of these theorems. Thank you.